Students, in the previous day we have discussed about noise in amplitude modulated signal. Today we will focus on the noise in the angle modulated signal, in phase modulated or in frequency modulated. This is the basic building block. This is the message signal. It is angle modulator, angular modulating the signal, that is the transmitter part. Channel noise added. This is the receiving section, consists of band pass filter, angle demodulator, balance filter, and finally we are getting the output from here. Obviously associated signal and noise power will be calculated. Now if we write the demodulated signal, here ST is A cos of omega ct plus psi t. This is the modulated angle which may comes from phase modulation, then it will be Kp into mt. If it is case of frequency modulation, then it will be integration of the message signal. Okay, this integration will be not. Now what is the noise at the input of the demodulator? That is whatever we have considered, band pass noise, NIT is NCT cos omega ct plus NS sin omega ct, where each one has the implication or notation as before. Here, in case of this angle demodulation in the presence of noise, the most important approximation or assumption lies here. See this part very carefully. For demodulated signal, what is our demodulated signal? A plus cos omega ct into psi t. Amplitude is capital A, and what is the phase part? That is psi t. And for noise, what is the amplitude? Amplitude is ENT, and what is angle? That is theta nt. What is the bandwidth of this psi t? If we consider this phase, that will be proportional to the message signal. That means xt will vary with the frequency of B, because it is proportional or integration proportional to the message signal. But here the noise has the one bandwidth of that of message modulated signal that is entering through the band pass filter. Therefore, as the bandwidth of a FM modulated signal is 2 into delta F plus B, so here 2 into delta F plus B, noise is also entering in that bandwidth and it is passed. Therefore, this ENT or theta NT varies very rapidly than that of psi t, because psi t bandwidth is B hertz. Here bandwidth is 2 into delta F plus B, where delta F is very much higher for higher than B for wideband spectrum. Okay, so this thing you should always keep in mind in angle modulation, that noise phase varies more rapidly than that of signal phase. Now write the expression of the demodulator input. It is YIT is A cos omega ct plus psi t, that means FM modulated signal plus the noise, and how the phasor has been drawn. This is A cos omega ct plus phi t. Here we are showing A, and the noise part ENT noise has been shown here. The resultant signal is shown here. The angle here is omega c plus psi t, omega ct plus psi t, and if we consider, if we represent the resultant signal, we can write RT into cos omega ct plus psi t plus del psi t. Okay, this is a representation procedure. So here this is the angle omega c plus phi t. This angle we are telling as omega ct plus theta nt. This will be important to calculate the noise when the noise is smaller. ENT is less than, very less than A. So I will calculate that. For that we will see, if ENT is small, if this noise phase is small, then we can approximate that del x is nothing but this line divided by this line. Okay, Therefore, for small noise, what will happen? del x will be this line divided by this line. Now we have to calculate this line. How we will get it? This angle is omega ct plus theta nt. So what will be the angle here? It will be theta nt minus psi nt. This angle will also be this difference of these two. Therefore, what will be that? Ent into cos of theta nt minus psi t will give me the length of this line. Okay, therefore del xt is this value ent cos theta nt minus psi t divided by a. That has been written, and we have done one approximation once again here with the same presumption that here theta nt minus psi t. Theta nt is the angle due to noise having bandwidth delta f plus b varying rapidly than that of psi t having bandwidth of beta. So over a time period we can consider that psi t is almost constant where theta nt is rapidly changing. Therefore psi t has been considered to be constant and psi, and we have done some calculation, and for this case we have also calculated the spectrum. This is the spectrum. You see the spectrum of the noise here. Interestingly, this is 2 into delta f plus b. Where it is? When it is entering the band pass filter or receiver. We can consider this band pass as NC or NS in quadratic form. We have seen from previous. And SXF will be what? The spectrum of this del xt. What will be the spectrum? That will be this square ns plus this square sin psi by a into spectrum of nc. That has been written here, and you see, and you can see it also from previous when a linear signal is transmitted to a linear system. What will be the output spectrum density? There I have shown it is nothing but hf square into sxf. So this is the calculation, but we see this is our power spectral density. Now you see this is the band pass filter having the bandwidth of 2 into delta f plus b, and here we have represented it in terms of delta f plus b sx del f. We have got it. Then it will be passed through a band pass filter, low pass filter, to get the message signal. What is the bandwidth of the message signal? B hertz. Therefore our interest of noise is confined to now the noise of B hertz bandwidth, not the whole delta f plus b. Therefore output noise is n divided by a square, but the bandwidth has been reduced to B, and output signal to noise ratio has been obtained by a kp square whole square m square divided by twice nb. Sorry, correct it. Therefore output SNR in terms of our benchmark notion gamma is kp square m square t into gamma, and finally we have obtained that signal to noise ratio is proportional to del of omega square. Okay, it is an interesting findings that in case of amplitude modulation we had very less control over the signal to noise ratio, but here we have the control that we can increase the signal to noise ratio but by enhancing del omega square. That means what? Frequency deviation. That means if we and what is the bandwidth? Bandwidth is nearly equal to twice del omega. Okay, so if we can increase the transmission bandwidth, then we can enhance the signal to noise ratio, and this is one of the trade-off area or thumb rule of communication engineering, that to get SNR better you must give higher bandwidth. There is trade-off. That means getting output SNR at the cost of higher transmission bandwidth. Now noise in frequency modulation, before that we have discussed, we were discussing about noise in phase modulation. Now the frequency modulation, we have done a very simple approach, that is we are using phase modulation, phase modulator to be at par with the previous calculation, but at the transmitting end we have integrated, then sent to phase modulator. As a result, we will get frequency modulated signal. At the receiving end, receiving by phase modulator, taking the derivative, we will get the message signal. Output SNR will be calculated from here. Therefore, same calculation, and what I was telling here, HF square ddt. See here, this is ddt, and what is the transfer function? J omega. Therefore, signal to noise, the signal to noise ratio, in the same way you can calculate the noise power, everything. Signal to noise ratio is coming 3 into del f by beta b square, that is the bandwidth of the message signal, into m square t mp square by gamma. Similarly, FM is also, if we increase the transmission bandwidth, we can get the more signal to noise ratio. Therefore, signal to noise ratio of phase modulation and frequency modulation is in the ratio of this. Therefore, whether will signal to noise ratio in phase modulation or frequency modulation will be higher, it is difficult to tell, because it depends on the property of the message signal, MP or MP dash. Okay, so this is all about the frequency and phase modulation. And overall, there is a problem of here also lies, that is threshold effect, that we are going to discuss for large noise cases. See what happens here. In case of the condition that this noise is very much higher than that of A, if it is so, then this del psi t will not be approximated to be constant, or will not be small. Here we have seen, if it is the amplitude of the modulated signal, that is A, and or the signal, and it is the magnitude of the noise, the resultant become this. We have considered in 3 conditions. One is noise is here noise, and here noise, and you see this del psi is now rotating around near about twice pi. Okay, and we have in graph we have shown for del psi t how it is happening, that at first it is constant, now there is a spike. That means signal noise power has increased, and it is staying for say few microseconds. Then again the signal power is higher than noise power, no problem. Again the noise power has been drastically increased than the signal. There also we will get a huge fluctuation, and the same thing will be happen for frequency. By taking the derivative, we will see the spike, the places where the noise is increasing in a large by a large for a certain time interval. Okay, and that's why at some time at FM we get some noise. Now here also the threshold effect occurred, and here this threshold effect of FM is more important than A. Okay, and here also we see if the beta, that means FM modulation deviation ratio is beta is 2, beta is 6. What we see, that when this gamma is above a certain level, then SNR is higher, no problem. But when this input signal to noise signal divided by NB is reducing than a certain level, signal to noise ratio drastically reduced. Therefore, we must ensure that with the increase of beta, that means with the increase of bandwidth. Okay, because if you increasing beta, that means what? You are increasing the frequency deviation, that means you are increasing the bandwidth. You are increasing the bandwidth because from the previous calculation we have seen that the output signal to noise ratio is proportional to bandwidth square. both in case of frequency modulation or phase modulation, frequency modulation del f square, and in case of phase modulation also output signal to noise ratio is proportional to the square, in both the cases square of the transmission bandwidth. Therefore, to get the output SNR, you are increasing the beta or del omega or del f or transmission bandwidth. But the problem is that when you are increasing the gamma, the value of gamma, that means threshold value, are also increasing. That means this is a beta equal to 2. Here from the output signal to noise ratio is drastically reducing, but when you increased the transmission bandwidth or beta, you see the gamma requires for good performance should be higher, because it has drastically the value of output signal to ratio started decreasing. Therefore, there should be some arrangement so that we can increase the bandwidth, and by the increase of bandwidth or frequency deviation we can increase the output signal ratio, but we must ensure that this output signal to ratio or the gamma does not enter into the threshold region. To have that, we use a method. We are not going to the details. I think it is not in your syllabus also. That is frequency compressive feedback. This demodulation will be used for frequency modulation or angle modulation or whatever may be. Basically, we have discussed about two demodulation. One is frequency discriminator and another is phase log loop. But this whenever there is a high chance of threshold, their demodulation of angle or phase or frequency is done by frequency compressive feedback, where we tactfully decrease the value of the, here you see, thus multiplying by small value implies that the yes. So what we see, the received signal beta is higher. That means wideband frequency. But we are doing something here. That means here we are considering that this is a frequency is omega 1, and PLL, in case of PLL, what we consider the frequency omega c, here also frequency omega c, but here we are considering difference, that here the frequency is omega c and it is omega c minus omega naught. Therefore it will generate some omega naught, and the calculation has been shown explicitly. You can easily understand that by selecting the value of two constant kV and kd, we can what we can do, we can have small value of beta to the input of the discriminator. Though the signal received is of wide band, the input going to the discriminator, that bandwidth is low, therefore there is lower chance of threshold. In that way we can make some trade-off of, and we can have higher bandwidth signal, higher output SNR with the less chance of threshold effect. For that reason also PLL is also preferred than that of frequency discriminator. Thank you.